Hello there, and welcome to the Sleepless Scientist, a quiet little refuge in the vastness of the night where thoughts can loosen, wander and drift, and where the mysteries of the universe arrive not with thunder, but with a soft whisper. Tonight, we're going to take a gentle journey into something that sounds simple at first, almost like a unit you might find in a dusty science textbook. And yet it carries within it distances so large they slip through our fingers the moment we try to hold them. We're going to explore the light year, the distance that quietly breaks our brains, reshapes our sense of scale, and reminds us how astonishing it is that we exist at all. But before you settle into this slow unravelling, I'd love to ask you a small favour. If you enjoy these calm wanderings into science, and if this kind of soft curiosity helps you rest a little easier, it would mean a great deal if you gently tap the like button or subscribe to the channel, only if it feels right, of course. And if you're still awake enough to type, tell me where in the world you're listening from and what time your night has chosen for you. It's always comforting to imagine people scattered across continents, some preparing for sleep, some lingering in the late hours, some just beginning their evening, yet all connected by the same quiet desire to understand a little more about the cosmos. For now, feel free to dim the lights, settle into whatever position feels most restful, maybe let the blankets rise a little closer around you. Let your breath slow, let the day fall away. And if your mind drifts during this journey, that's perfectly fine. These ideas will still be here, floating softly through the dark. Tonight, we begin right where you are, on Earth, a place small enough for morning commutes and evening walks, before letting the scale stretch outward, farther and farther, until it reaches distances so large that ordinary words, ordinary numbers and ordinary intuition quietly fall apart. This is a story of distance, but also of perspective, and of what it means to live in a universe where even the nearest stars are oceans away. Let's begin. When you step outside your door and walk to a nearby shop, your mind knows exactly what that means. A few hundred meters, a couple of minutes, the rhythm of your footsteps, the feel of the pavement beneath your shoes. Even if you travel farther, across a city by motorbike or car, or to a nearby province, the distance still fits comfortably inside the mental map your brain evolved to understand. We are creatures shaped by villages, forests, footpaths and horizons only a few kilometers wide. Our ancestors rarely needed to imagine more than a trek across a valley or the span of a river. Even the entire circumference of Earth, about 40,000 kilometers, sounds large but still belongs to this intuitive world. You can imagine circling it on a plane, or at least imagine that it could be done in a day if you stayed in the air long enough. Kilometers and meters are friendly, familiar. They tell us how far, how long, and how much effort we need to spend. But something strange happens when we step beyond this planetary comfort zone. The first place most of us look is the moon. It's right there in the sky, gentle, pale, almost close enough to touch with a thought. Yet the distance to the moon, 384,000 kilometers, is already far beyond what imagination likes to hold. If you drove a car steadily at highway speed without stopping day and night, you would need several months to get there. And that's the nearest celestial neighbour we have. Then there's the sun. At roughly 150 million kilometers away, the numbers stretch so far that they stop being distances and become abstract shapes made of digits. The sun's light, travelling over 300,000 kilometers every second, fast enough to circle Earth more than 7 times in a single heartbeat, still needs more than 8 minutes to reach us. 8 minutes for something moving at the universe's supreme speed. If sunlight itself takes that long, what hope does anything slower have? Even the fastest spacecraft ever built by humans struggle in this vastness. The Apollo missions, which once carried astronauts to the moon, travelled at around 11 kilometres every second. To us that sounds impossibly quick, faster than anything you'll ever ride, faster than anything you'll ever see, and yet, in the language of the cosmos, it is barely more than a quiet drift. Even the Parker Solar Probe, the current record holder, moving so fast it seems to skim the sunlight itself, would still take thousands of years to reach the nearest star. This is where our minds begin to falter. Numbers grow large, and our intuition, built for fields and mountains, cannot stretch enough to keep up. Our mental sense of distance, so reliable at home, begins to slide off the edge of familiarity. The truth is simple, yet unsettling. The human brain did not evolve to understand the scale of the universe. Our ancestors didn't need to imagine millions of kilometres. They needed to remember where the river bends, where the berry bushes grow, where the animals migrate. Their world was intimate and immediate, and our inner sense of distance still echoes that ancient scale. And yet, despite this limitation, we've built machines to cross space, telescopes to map distant galaxies, and minds capable of contemplating distances so large they bend understanding itself. We stand on a planet small enough for evening strolls, yet we gaze across a universe where even a single sunbeam needs 8 minutes to arrive. As we drift further into this journey, we will gently widen the frame, letting the numbers grow, letting the distances stretch, and watching as our intuition quietly gives way to a new kind of understanding, one born not from instinct, but from wonder. There is a moment, somewhere just beyond the edge of Earth's atmosphere, when our familiar sense of distance begins to loosen its grip. Down here, kilometres behave. They feel like something we can imagine, something we can divide into minutes and hours and fuel and effort. But the farther we travel into the quiet of space, the more those same units begin to stretch, thin, and weaken, like a thread pulled too far across a vast surface. Tonight, we'll drift into that strange territory where the numbers keep growing, but our intuition stops growing with them. Let's begin with a distance that seems manageable, the space between Earth and the Moon. It's a number most people have heard at some point, roughly 384,000 kilometres. It sounds large, but not impossible. If you could drive non-stop at a comfortable highway pace, you might think of it as a road trip lasting a few months. Astronauts in the Apollo missions crossed it in about 3 days, riding atop engines that roared so powerfully they shook the ground beneath them. And yet, once you imagine this journey in more detail, the mind begins to slip. 384,000 kilometres is not far in any earthly sense. It is a gulf so broad that even our language feels shy around it. The Moon hangs so close in our sky, and yet its distance is more like travelling around Earth nearly 10 times. Still, the Moon is in our cosmic backyard. The real unravelling begins when we step outward toward the Sun. The distance to the Sun is roughly 150 million kilometres, a number so large it starts to behave more like a horizon than a measurement. You can try to picture it. You can imagine driving or flying, but the mind eventually balks. It's like trying to imagine carrying the ocean in your hands. At this scale, the numbers become less like distances and more like abstract sculptures made of zeros. And yet, we know this distance because sunlight tells us. A beam of light leaves the sun's surface and races toward us at a speed so astonishing it seems almost fictional, around 300,000 kilometres in a single second. Even so, even moving with the universe's supreme speed, that beam needs just over 8 minutes to reach Earth. 8 minutes for something so fast it can loop around Earth more than 7 times before you can take a deep breath. Imagine standing on a quiet shore, watching a wave form far across the sea, knowing it will reach you minutes later. Sunlight is like that wave, except the sea is utterly silent, and the wave travels faster than anything your mind has ever known. As distances increase, a quiet transformation happens. Kilometers stop being friendly. They stop behaving like the steps of a journey. Instead, they become almost invisible, so large, so numerous, that they no longer carry feeling. They become too big to picture. It's similar to how your mind can understand the idea of 1,000 grains of rice, but once the number climbs into millions or billions, the image collapses. Our brains simply weren't built for such magnitudes. We can recite the numbers, but cannot live inside them. Spacecraft reveal this quiet failure of intuition. The Apollo spacecraft travelled at more than 11 kilometers each second, a speed far beyond anything you might experience on Earth. Most of us will never travel fast enough to cover even 1 kilometer in a single heartbeat, but Apollo covered 11. And yet, even at a speed that once carried humans to the moon, a journey to the sun would take months. A journey to the outer solar system would take years. The spacecraft becomes a tiny spark drifting among distances that treat human engineering like a gentle whisper. Then there is the Parker Solar Probe, the fastest object humanity has ever built. It moves at more than 600,000 kilometers every hour, a velocity so immense it is easiest to describe in images rather than numbers. Picture a spacecraft skimming the inner edge of the sun's domain, almost surfing on heat and light, diving closer with each orbit as if slipping through the fingers of gravity itself. Even at that speed, even at a pace that seems impossible, the nearest stars remain breathtakingly far away. It would take tens of thousands of years to reach the closest one. Here, in these enormous figures, kilometers reveal their limits. They were never meant for this. They are perfect for Earth, for roads, for commutes, for measuring the length of a river. But space is not shaped for kilometers. Space is shaped for something else. Distances so large that light, the fastest messenger in existence, becomes the only tool that still makes sense. Light travels far enough, fast enough, regularly enough, that its journey becomes the ruler of the universe. This is the point where physicists gently set kilometers aside and bring in a new idea, one born not from walking or driving or flying, but from watching light itself move across the dark. They follow light for 1 second, then for 1 minute, an hour, a day, a week, a month, a year, and they ask, how far has it gone? That is the moment when distance flips into a new form, a form large enough and calm enough to hold the universe. The moment when kilometers stop making sense is the same moment when the light year begins. Before we drift toward that idea, pause for a moment and consider how quietly our intuition breaks here. Our entire sense of distance, every instinct we've ever had, works beautifully on Earth. But space is wider, deeper, stranger. It carries numbers that slip through our hands no matter how gently we hold them. Kilometers were made for us. Light years were made for the universe. And to understand the cosmos, we must learn to let one go and embrace the other. As this thought settles, we can begin to follow the path of a single beam of light, moving through the dark with perfect speed, carving out a new kind of measurement, one built not on footsteps or engines, but on the steady heartbeat of the universe itself. If you step outside on a clear evening and lift your eyes toward the sky, you might notice something subtle about the stars overhead. They don't feel impatient. They don't feel hurried. Their glow seems steady, almost serene, as if the light has all the time in the world to reach you. And in a way, it does. But behind that gentle glow lies something astonishing. Light is not simply fast. It is so fast, so effortlessly swift, that ordinary comparisons collapse under its feet. To understand the universe, we have to understand this messenger, what it is, how it moves, and why nothing can outrun it. On Earth, we measure speed in ways that make sense to our daily lives. A brisk walk might carry you a few kilometers in an hour. A car might travel 100 kilometers in that same time. An airplane can cross entire countries in just a few hours. All of these speeds feel meaningful because we have lived them. But light exists at a scale that has nothing to do with footsteps or roads or runways. Light travels about 300,000 kilometers in a single second. Imagine snapping your fingers. In that short, effortless click, light has already zipped around Earth more than 7 times. The distance it covers in one heartbeat is greater than any journey you've made in your entire life. It moves with such effortless certainty that it almost seems like cheating, as if the universe gave light a special permission to ignore the limitations the rest of us must obey. This speed is not accidental. It is woven into the fabric of reality. No object with mass, no matter how much energy you pour into it, can ever reach the speed of light. Instead, as something approaches that speed, it requires more and more energy, like trying to push through a wall that grows thicker the harder you try. Light, however, has no mass. It glides through this cosmic limit effortlessly, slipping through the universe as if moving along a perfectly greased path. Because light moves so quickly, it becomes a perfect ruler for the cosmos. Its speed does not change. Whether it's passing through the emptiness between galaxies, through the atmosphere, or through the glass of your window, its pace remains steady. It is the universe's most faithful constant. And yet, despite its unimaginable speed, even light needs time to travel. When you look at the sun, you're not seeing it as it is right now. You're seeing it as it was just over 8 minutes ago. The time it takes sunlight to cross the 150 million kilometers of space between Earth and its parent star. If something remarkable happened on the sun this very moment, you would not know it until more than 8 minutes later. The moon, much closer, sends light that takes only about 1 second and 1/3 to reach us. But even that short delay means you're looking slightly into the past every time you glance at it. These delays aren't just abstract curiosities, they shape how we explore the solar system. When engineers send signals to a rover on Mars, the messages cannot arrive instantly. Depending on the positions of Earth and Mars in their orbits, that delay can range from a gentle 2 minutes to a nearly coffee break length 22 minutes one way. Imagine trying to control a remote-controlled car, but having to wait almost half an hour before it responds to a simple left turn. This is why Mars rovers must be patient and clever. They cannot rely on quick commands from Earth. They must make small decisions on their own. They must be cautious explorers, moving slowly, scanning the terrain, thinking carefully because they cannot ask questions and receive immediate answers. Light, with all its speed, creates a kind of quiet lag in our conversations with distant machines. And yet light does much more than communicate. It carries stories. When you look at the stars, you're seeing messages that have crossed impossible distances with perfect grace. The light from a nearby star might be a decade old by the time it touches your eyes. That means you're looking not at what the star is doing now, but at what it was doing years ago. Light travels through the universe like a tireless historian, bringing ancient information to new worlds. Light also tells us how far things are, not through complicated symbols or chalkboard equations, but through gentle, observable patterns. When stars move relative to Earth, their light stretches or compresses. Starlight stretched into deeper red tones tells us that the star is moving away. Starlight compressed toward blue tones tells us it is moving closer. It is like listening to a train whistle rise and fall in pitch as it approaches and recedes. The universe hums a similar tune, only instead of sound waves, it uses light. This simple stretching and squeezing allows astronomers to measure the motion of distant galaxies, to map the expansion of space itself, and to determine how far away ancient light must have travelled. Light becomes not only a messenger, but a compass, a ruler, and sometimes a clue left behind by a cosmic event so old that all other traces have vanished. Even the idea of a light year, the distance light travels in one full year, comes from watching light's journey unfold through time. It is not a measure we invented at random. It is the universe offering us a natural scale, one built from the only thing swift enough to cross interstellar distances in a meaningful span. Because of this, light years are not just units of measurement. They are the rhythm of the universe. They are the way the cosmos tracks its own history. Every beam of starlight is a traveller carrying news from across time and space. Some of these messengers began their journey before humans walked upright. Some left their home stars before Earth itself existed. And yet, after millions or billions of years of silent travel, they arrive gently on your retinas without a hint of exhaustion. So when we talk about light as the fastest thing in existence, we are not just speaking of speed. We are speaking of constancy, of patience, of the way light quietly becomes the bridge between what is, what was, and what may never be again. It is the universe's most devoted traveller, and everything we know about the cosmos is written in its glow. In the sessions ahead, we'll follow that traveller a little farther. Each step will bring us closer to understanding why the universe is measured not in kilometres, but in the silent footsteps of light. If you've ever heard someone say that a star is 10 light years away, you might have nodded politely, feeling that you understood, while a quieter part of your mind whispered, "I know what the words mean, but I don't actually feel what that distance is." This is one of the gentle mysteries of the universe. The light year is a perfectly sensible idea, yet almost impossible for our intuition to hold. Tonight, we're going to slow that idea down and let it unfold softly, one small step at a time. The best place to begin is not with a year, but with a second. A single second is small enough to grasp. You can breathe in a second, blink in a second, snap your fingers in a second. In the time it takes to perform that tiny action, light has already moved 300,000 kilometres. That's the entire width of your country, multiplied many times over, gone in the blink of an eye. If Earth were a circle on a sheet of paper, light would loop around it 7 times before your mind even completed a thought about it. From there, we can stretch the idea gently. If light travels 300,000 kilometres in 1 second, then in 1 minute, 60 of those gentle heartbeats, it covers 60 times that distance. Suddenly we're not talking about a journey across a planet, but a journey that slips deeper into the quiet darkness of space. After an hour, light has crossed even more, travelling farther than any spacecraft humanity has ever launched. At this point, the numbers start to grow so quickly that they begin drifting out of reach. So instead of focusing on the numbers themselves, let's imagine light as a small, tireless traveller. It leaves its home star and without slowing begins to glide through the dark. It doesn't rest. It doesn't question. It simply moves, second after second, minute after minute, hour after hour, carried forward by a rule built into the universe itself. After 1 day of this journey, our traveller has crossed a distance so large that kilometres start to feel like grains of sand dropped into an ocean. After a week, it has travelled farther than our entire solar system from end to end. After a month, farther still, drifting through regions where planets are no more common than lonely lanterns scattered across a nearly empty plain. Then comes a year a full year of uninterrupted motion, a full year of gliding silently through the cosmos, never pausing, never growing tired. At that moment, the traveller has covered roughly 9,460,000,000,000 kilometres. That number is so large, so unwieldy, that even saying it out loud barely makes a dent in understanding. It's like trying to imagine every grain of sand on a beach or every leaf in a forest. Your mind can hear the number, but it cannot hold it. This vast distance, 9,460,000,000,000 kilometres, is what we call a light year. Not because it measures time, but because it is the only distance large enough and natural enough to make sense in the universe. A light year is how far light travels in 1 year. Nothing more, nothing less. It is a distance built not from human experience, but from the rhythms of the cosmos. To truly feel how large it is, imagine walking a single kilometre, a casual stroll. Then imagine taking that same stroll 2 kilometres, 5, 10. Perhaps you can picture a full marathon, 42 kilometres, or the length of your city from one end to the other. Now imagine doing that walk 9,460,000,000,000 times, each time 1 small kilometre, each time the same step over and over. That is 1 light year, not in theory, but in reality. Kilometres, metres, even the idea of distance as we know it. All of these concepts are dwarfed by the sheer immensity of light's yearly journey. This is why astronomers set aside the units we use for daily life. The universe refuses to fit into those boxes. Instead, it stretches outward in distances so large that only light, with its perfect pace, can measure them without breaking. There's another important part to this story. When we say a star is 10 light years away, we're not only describing distance, we're also describing time. The light now reaching your eyes left that star a decade ago. If the star flickered or changed, or even died in the present moment, that news has not yet reached us. We are always seeing the universe not as it is, but as it was. This built-in time delay is not a flaw or a barrier. It is a quiet gift. It means that a single glance at the night sky allows you to see across centuries, millennia, even millions of years. Every star is a tiny time machine. Every faint shimmer of light carries a story that began long before our species existed. Light years become more than measures of space. They become measures of memory, of ancient moments still travelling toward us through the dark. Alternatively, consider this image. Imagine you are standing at the shore of a calm lake at dusk. A lantern is lit on the far side, its reflection trembling across the surface. You see the glow instantly because the lake is small. Now imagine that same lantern, but millions of lakes away, with the water stretching into a darkness that seems to have no edge. If the lantern were lit in that far place, its glow would still reach you, softly, patiently, but only after a long, long journey. That is what it means for sunlight, starlight, and galaxy light to arrive at Earth. We live in the shimmer of lanterns lit across the ages. This is why understanding the light year changes how we think about the universe. It is not a number meant to intimidate. It is a reminder that space is vast, time is deep, and everything we see is part of a gentle, ancient unfolding. The light year teaches us that the universe is not just wide. It is layered, patient, and rich with echoes of the past. As our journey continues, we will follow this idea outward toward planets, stars, and the borders of our cosmic neighbourhood, allowing each step to reveal more of what it truly means to live in a universe measured by the footsteps of light. There is a moment in every conversation about space when people nod along, happy, curious, following the thread, and then suddenly the numbers become so large that the thread slips away. You may understand what 1,000,000 means. You may have a sense of what 1 billion represents. But once the conversation expands into the realm of trillions, your mind quietly steps back, shakes its head, and says, "I'm listening, but I can't truly picture this anymore." It's not a failure of intelligence. It's simply that the human brain evolved to measure distances you can walk before sunset, not distances that light needs a year to cross. So tonight, before we stretch any farther, we're going to bring these enormous numbers down into the soft human world of seconds and breaths and heartbeats, places where your intuition still works. Because once you understand what a million, a billion, and a trillion feel like, you begin to understand why the light year is not just large, but almost mythic. Let's start gently with 1,000,000. If you began counting one number per second, how long would it take you to reach 1,000,000? It sounds like something you might finish in an afternoon if you concentrated hard enough, but the truth is more surprising. Counting to 1,000,000 would take a little over 11 days. 11 days of counting one number per second without sleep or distraction. You'd watch the sun rise and set 11 times before reaching that final number. But even then, 1,000,000 is still within the realm of the imaginable. You could take a long walk every morning and picture each step as another count toward your million. Now let's lift this one gentle step higher. What about 1,000,000,000? If you continued counting still one number per second, you wouldn't finish in 11 days. You wouldn't finish in 11 months. You would need more than 30 years. 1,000,000,000 seconds is longer than many human lifetimes. You might begin counting in your 20s and finish in your 50s. Suddenly 1,000,000,000 feels less like a number and more like a stretch of human history. Then comes the number that quietly breaks our intuitive map of reality, the trillion. 1,000,000,000,000 seconds is not a few decades. It is more than 31,000 years. If you started counting one number per second during the last ice age, you would still be counting today. Cities did not exist when you began. Written language had not yet been invented. Mammoths walked under cold skies. Human civilization itself is younger than 1,000,000,000 seconds. Now, hold that feeling gently in your mind. 1,000,000,000,000 is not simply the next step after 1,000,000,000. It is a completely different landscape. A landscape so large that our memories, our stories, and our entire species sit inside it like small stones in a desert. And yet, to understand a single light year, the distance light travels in 1 year, you must imagine not 1 trillion, but roughly 9 trillion, 460 billion kilometers. A distance so immense that it takes the amount of walking you could do over the course of all human history, multiplied by vast amounts, just to cross it once. This is why the idea of the light year always feels slippery. Our brains are not built to picture trillions of anything. We can talk about them, we can name them, but we cannot hold them. Even the number of leaves in a massive forest or grains of sand on a long beach falls short of 1,000,000,000. The scale we're entering now is cosmic, not earthly. To make the idea softer, imagine this picture. Take 1 kilometre, a distance you could walk in perhaps 12 minutes at a relaxed pace. Now imagine doing that walk several times a day for the rest of your life. 10,000 walks. 100,000 walks. Imagine all the kilometres you've ever walked, every commute, every errand, every childhood adventure. Now multiply that number by 1,000,000,000. That gives you only part of what 1 light year represents. It might feel overwhelming, but this is actually where the beauty begins. Because the universe, knowing that our minds are not made for these staggering distances, offers a simple, natural tool to help us understand it: light. Light moves with perfect consistency. It doesn't speed up or slow down. It doesn't tire or change its mind. It travels 300,000 kilometers every second, no matter where it is or what it's passing through. And because it does this, we can build the idea of a light year entirely from gentle increments that your mind can follow. Start with a single second. Light travels 300,000 kilometers. That's the foundation. Add 60 seconds, and in 1 minute it travels 60 times that distance. Add 60 minutes, and in 1 hour it travels a distance so enormous that we already begin drifting out of the solar system in our imagination. In 1 day, it has crossed the vast emptiness where planets drift like small islands. In 1 week, it has left even the farthest planets behind. In 1 month, it travels so far that our language struggles to keep up. And then, in 1 year, it completes its journey, creating a distance large enough to navigate not just the solar system, but the space between stars. That final number, that enormous span of nearly 10 trillion kilometers, becomes a light year, a unit so naturally suited to the universe that it feels as if space itself suggested it to us. This is precisely why astronomers rely on light years instead of kilometers. Kilometers are too small, too terrestrial. They crumble under the weight of cosmic distances. But light years, born from the steady heartbeat of the universe's fastest traveller, hold these distances comfortably. Once you understand that scale, once you feel the difference between 1 million, 1 billion, and 1 trillion, you begin to understand why stars that look so close together in the sky are actually separated by oceans of emptiness. You understand why space feels quiet, why messages sent across the void take years to arrive, why the nearest star might as well be a distant country you can see, but never reach with any vehicle you've ever known. And most importantly, you understand why the universe, with all its radiant beauty, is also a place of deep patience. Light takes its time, stars wait, galaxies drift, and we, tiny creatures on a small blue world, learn to measure the cosmos not through instinct but through wonder. As we continue our journey, this sense of scale will become the foundation for everything that follows. Distances to planets, to stars, to galaxies, even to the farthest edge of the observable universe. Each new layer will rest gently on the one beneath it, forming a picture as vast as it is peaceful, a universe where light itself becomes our guide. When astronomers tell you that a star is 40 light-years away, or that a galaxy lies 200 million light-years from Earth, it is easy to imagine they pulled those numbers from some brilliant equation written in chalk on an enormous blackboard. But the truth is gentler and far more human. Measuring the universe is not done through towering formulas or dense symbols. It is done through patterns, soft, patient, and surprisingly familiar patterns. Patterns your eyes already know from everyday life. Tonight we will climb what astronomers call the cosmic distance ladder, but we will climb it slowly without any mathematics, placing our feet only on the most intuitive rung each time. The first step is something so simple that children notice it without being taught. The way nearby objects seem to shift against distant backgrounds when you move your head. If you hold out your hand in front of your face and close one eye, your hand appears to shift slightly when you switch to the other eye. It's a tiny jump, a gentle sideways slip of the fingertip. This little motion is called parallax, though the name is far less important than the sensation itself. Astronomers use this same effect to measure the distance to nearby stars. Instead of switching eyes, Earth moves from one side of its orbit to the other over the course of 6 months, giving us 2 slightly different perspectives. The nearest stars shift ever so slightly against the unmoving backdrop of distant galaxies, just as your hand shifts when viewed by your left eye and then your right. By measuring how large or small this shift appears, astronomers can determine how far away the star must be. It is not a trick. It is a cosmic version of something you've already experienced 1,000 times without thinking. This method works beautifully for stars relatively close to us, those within a few hundred light years, but as we look farther into the night, the shifts become so small that they disappear. It's like trying to see the movement of a tree on a faraway mountain by blinking one eye and then the other. Beyond a certain point, the movement is simply too tiny, so astronomers climb to the next rung on the ladder. Here, they turn to a kind of star that serves as a natural cosmic lighthouse. These stars, known in scientific language as Cepheid variables, have a lovely predictable behaviour. They pulse. They brighten and dim in a steady rhythm, like someone breathing slowly in their sleep. The length of this pulse, the time between each brightening and dimming, tells us how powerful the star truly is. A longer pulse means a stronger, brighter star. A shorter pulse means a gentler glow. Because the rhythm reveals the true brightness, astronomers can compare that brightness to how faint the star appears from Earth. If it looks much dimmer than it should, we know it must be far away. It's a little like hearing a friend's voice across a field. If you know how loudly they speak up close, you can tell how far away they are by how softly their voice reaches you. This method allows us to measure distances across our entire galaxy and even into nearby galaxies. The universe, quietly and generously, offers us these natural beacons, stars that announce their distances through slow, steady breathing. But beyond those nearby galaxies, even the steady pulse of a Cepheid becomes too small to guide us. The next rung on the ladder belongs to something more dramatic. Moments when stars explode in a powerful burst of light. Certain types of supernovae, especially the ones astronomers classify as Type 1a, shine with almost identical brightness every time. These explosions are among the universe's most reliable distance markers. When one appears in a distant galaxy, astronomers can compare how bright it looks to how bright it ought to be, and from that they can infer the galaxy's distance. It's a little like seeing fireworks from across a city. If you know how bright the explosion truly is, then the faintness of the spark helps you estimate how far away the celebration must be. At this point, the ladder has taken us farther than our eyes can comfortably imagine. Parallax got us to nearby stars. Pulsing stars carried us across the galaxy. Exploding stars guided us to distant islands of light far beyond. But to measure the universe on its larger scales, distances between clusters of galaxies stretching across hundreds of millions or billions of light years, we need one final rung. This rung is hidden not in brightness or motion, but in colour. When a star or galaxy moves away from us, its light stretches into deeper, redder tones. When it moves toward us, its light compresses into bluer tones. It is similar to the way the sound of a passing train shifts in pitch as it approaches and then recedes. You don't need to understand the mathematics behind it to feel the idea. Motion changes the wave, whether the wave is sound or light. Because the universe itself is expanding, nearly all distant galaxies are moving away from us. Their light grows redder as space stretches around them. The farther away a galaxy is, the more its light is stretched. By measuring this soft shift toward the red, astronomers can estimate the galaxy's distance, even when that distance is so enormous that no other method can reach it. What begins as a tiny flicker of colour in a telescope becomes an echo from across unimaginable expanses of time. The same light that was born in a distant galaxy millions or billions of years ago continues its patient journey across the universe, carrying in its colour the story of how far it has travelled. This ladder, parallax, pulsing stars, supernovae and stretched light may sound like a series of complicated techniques, but each one is built from gentle, familiar ideas. Seeing something shift when you move, noticing a rhythm, recognizing a dimming, hearing a change in tone. None of them require formulas to feel real. They are simply the universe and the human mind meeting halfway. And once each rung is used to build upon the next, we end up with a way to measure distances so vast that even trillions of kilometers feel small by comparison. These tools allow us to map the universe not as an abstract set of numbers, but as a living, evolving landscape, one where every beam of light carries meaning, and where every distance is a patient story unfolding silently across the dark. As we continue forward, this ladder will give us the confidence to explore the outskirts of our solar system, the nearest stars, and eventually the swirling arms of our galaxy. Each new distance will feel less like an impossible number and more like a natural extension of the universe's quiet rhythm. If you have ever used a walkie-talkie, you might remember the tiny pause between speaking and hearing the reply, a momentary delay that feels almost like the air itself is thinking before it passes the message along. Now imagine stretching that delay across millions of kilometers. Imagine the space between your words and the response growing longer, not because anyone is hesitating, but because the messenger, light itself, needs time to travel. This gentle but profound delay shapes everything we do beyond Earth, and tonight we'll drift through the quiet truth of what it means to send instructions into the dark. Let's begin with Mars, a world close enough to appear in our sky, yet far enough to challenge every intuition we have about communication. When Earth and Mars are nearest to one another in their orbits, the distance between them is still so large that a message travelling at the speed of light needs about 2 minutes to make the journey, and when they drift to opposite sides of the Sun, that same message can take more than 20 minutes to arrive. If you sent a signal telling a rover to move forward, you might wait nearly half an hour for a confirmation. And if the rover encountered a rock or a sudden slope during that time, it would have to figure things out on its own. This delay is not because our technology is slow. It is because the universe is immensely large and light. Even with all its astonishing speed, still needs time to cross it. So every instruction to a rover becomes less like pressing a button and more like sending a letter across a quiet ocean, trusting that by the time it reaches the other side, your message will still make sense. That is why rovers like Curiosity and Perseverance behave less like remote-controlled cars and more like polite, cautious explorers. They receive a set of instructions each morning, plan their tasks for the day, study their surroundings, and even make small decisions when necessary. They move slowly, not because their wheels are weak, but because each choice must be deliberate. Instant reactions are impossible when even a conversation requires patience. Farther out, these delays grow longer. When the Cassini spacecraft orbited Saturn, a world more than 1 billion kilometers from home, light needed over an hour to travel between Earth and the spacecraft. A simple request like, "Turn your camera to the left," took more than an hour to deliver and another hour to receive the response. It was like having a conversation across a vast desert, where each question and answer echoed back only after long contemplative silence. By the time we talk about Voyager 1, the most distant human-made object, the delay grows into nearly an entire day. A message sent now will drift outward through the solar system for many hours before Voyager even receives it, and the reply will spend the same amount of time coming back. We communicate with Voyager as if speaking to someone in a deep, isolated valley, calling out and waiting for the echo to return long after our own voice has faded. What makes these delays so quietly profound is not just the inconvenience they cause, but what they reveal about our place in the solar system. Even in this relatively small neighbourhood, just our Sun and its orbiting planets, we're already dealing with distances so vast that the fastest thing in existence cannot cross them instantly. Light itself slows down, not in speed, but in meaning, because its journey requires us to wait, to listen, to breathe. These delays also shape how we explore. On Earth, if a machine malfunctions, we can intervene instantly. In space, by the time we learn something has gone wrong, the moment to react may have already passed. Engineers designing spacecraft must imagine every possible failure and craft systems that can correct themselves without waiting for help. Spacecraft become not just machines, but quiet thinkers, capable of diagnosing their own problems in the silent gaps between messages. The light time delay transforms even simple acts, turning, moving, taking a picture, into exercises in trust. A mission team sends instructions into the darkness, hoping each command lands gently, hoping the machine understands, hoping that nothing unexpected lurks just out of sight. And when the picture finally returns, minutes or hours or even a day later, it feels like receiving a postcard from a distant friend. These delays also explain why certain styles of missions are impossible. We cannot drive a rover on Mars the way we would steer a radio-controlled car in a field. We cannot pilot a spacecraft through the rings of Saturn in real time, dodging icy debris with quick reflexes. If we tried, our reactions would always arrive too late. Even with perfect skill, we would be outpaced by the very distance we're trying to explore. Space in this sense demands humility. It asks us to slow down, to plan ahead, to trust our machines, and to accept that communication across cosmic distances is always softened by time. As technology advances, we build more autonomous systems, rovers that can choose safe paths on their own, spacecraft that can adjust their trajectories without waiting for commands. But the universe remains unmoved. The speed of light stays constant. No amount of engineering will ever change the fact that the solar system is huge, and the spaces between its worlds stretch farther than our instincts can comfortably comprehend. And yet, there is something peaceful in this delay, something almost meditative. The patience required to send a signal to a distant spacecraft invites a different way of thinking. You cannot rush space. You cannot force the universe to hurry. All you can do is send messages with care and wait for their return, allowing the rhythm of light to set the pace. In the grand scheme of things, these delays are teaching us something profound. Even within our own solar system, communication unfolds not at the speed of desire, but at the speed of nature. Light, for all its perfection, asks us to be gentle, to be patient, and to accept that exploring the cosmos means making peace with distance. As we drift deeper into our journey, these delays will become a stepping stone for understanding even greater separations, distances not just measured in millions or billions of kilometers, but in years of light's travel across the silent expanse. If you were to look at a diagram of the solar system in a textbook or on a classroom wall, you might see the planets lined up like beads on a string, each spaced with polite gaps in between. Mercury close to the Sun, Venus tucked just behind it, then Earth, then Mars, and farther still the graceful arcs of Jupiter and Saturn, followed by the distant icy worlds of Uranus and Neptune. These diagrams are neat and orderly, almost comforting, but they're also gentle illusions, maps designed to fit on a page rather than truthfully depict the sheer emptiness that fills our cosmic neighborhood. Tonight, we're going to step into the real solar system. Not the tidy one on the wall, but the vast, quiet ocean of space where planets drift like small lanterns separated by unimaginable darkness. Begin with the Sun, the warm anchor of our sky. It feels enormous when you imagine it above the horizon, glowing with a light that nourishes life on Earth. But in the true scale of the solar system, the Sun is a single campfire in the middle of a desert so large that even light needs minutes or hours to cross it. It takes just over 8 minutes for sunlight to reach Earth, which already feels like a long time if you imagine light as the fastest traveller in existence. But the farther you go from the Sun, the longer this journey becomes. Light needs more than half an hour to reach Jupiter. It needs nearly 5 hours to reach the edge of the region where the major planets orbit. Imagine a messenger so swift it circles Earth 7 times in a second, and then imagine that same messenger taking almost half a day to reach the solar system's frontier. This is the first hint that our solar system is not merely big, it is spacious, a word that suggests comfort, but here means something closer to solitude. Space does not fill itself with planets the way forests fill themselves with trees. Instead, it stretches outward with vast, dark plains, where even the closest neighbours remain incredibly far apart. Take Earth and Mars, for example. Even when they line up at their minimum distance, they are still separated by more than 50 million kilometres. When they drift to opposite sides of the Sun, that distance swells to over 400 million kilometres. If you picture Earth and Mars as 2 boats floating on a lake, the lake suddenly becomes an inland sea, and then a great ocean, and then an expanse so large that even light, the swiftest sailor imaginable, needs long minutes to cross from one boat to the other. And yet, in most maps, Earth and Mars look as though you could point from one to the other with a fingertip. As we move outward, this illusion becomes more pronounced. Jupiter, for example, is often drawn only a short hop beyond Mars, but the real gap between Mars and Jupiter is larger than the total span of the inner planets combined. It's as if the inner solar system, the realm of Mercury, Venus, Earth and Mars, is a small cluster of islands close to shore, and Jupiter lies far across the open sea, barely visible through the haze. When spacecraft travel from Earth to Jupiter, they do not soar gracefully from one bright world to the next. They drift for months and years through emptiness before arriving at a giant orb surrounded by swirling storms. Even the outer planets, all grand and majestic in pictures, float in territory so wide that the distances between them dwarf everything closer in. Saturn, with its luminous rings, lies nearly 1.5 billion kilometres from Earth. Light, moving at its incredible pace, still needs more than an hour to make the trip. Neptune, the farthest of the classical planets, sits almost 30 times farther from the Sun than Earth does. Imagine the Sun as a glowing lantern in the centre of a dark field. Earth would be a small circle nearby. Neptune would be so far away it would barely feel the lantern's warmth. And beyond Neptune lies an even quieter realm, the Kuiper Belt, a region filled with icy rocks and dwarf planets. Many of these worlds drift through the dark like forgotten marbles scattered at the edge of a playground. Some are smaller than cities. Some are as wide as continents. Some move in strange, elongated orbits that take centuries to complete. And all of them exist in a place where the Sun is no longer a bright star but a pale, distant glow, more like a large planet than the powerful furnace we know from home. Still farther out, there is the heliosphere, an enormous bubble carved into space by the solar wind, the stream of particles flowing from the Sun. The edge of this bubble, known as the heliopause, is not a solid boundary, but a blurry frontier, where the influence of our star fades and the vastness between stars begins. Voyager 1 crossed this frontier in 2012, becoming the first human-made object to enter what astronomers call interstellar space. Yet even here, even at the very edge, it remains only a single light day away from Earth. One light day, a distance that feels immense in human terms, but compared to the 4 light years separating us from the nearest star, it is barely a first step. This contrast is quietly astonishing. The solar system is so enormous that our fastest spacecraft need decades to cross it, and yet, in the scale of the galaxy, the solar system is only a tiny fragile bubble floating in an ocean thousands of times larger. Even light, our swiftest companion, can barely make a dent in the distances that lie beyond. All of this reveals a gentle truth. The solar system is not crowded. It is lonely. The planets do not sit together in a circle like friends at a table. They drift alone, separated by expanses so vast that our instincts fail to capture their enormity. When we send missions into space, we're not navigating a busy streetscape. We're sailing through a quiet sea where distances stretch into the night like endless waves. Yet there is something strangely peaceful about this, something almost calming. The empty spaces between the planets are not barren, they are serene. They give room for thought, for silence, for the soft hum of photons travelling outward at the universe's only true speed limit. As we drift into the next sessions, this realization, the sheer emptiness of our own cosmic neighbourhood, will help us understand why the nearest stars are so difficult to reach, and why the light year becomes not just a measurement, but a reminder of the universe's deep patience. When you stand beneath a clear night sky and look upward, the stars appear sprinkled almost generously across the darkness. They seem close enough to touch with a thought, as if you could pluck one from its place like a firefly resting on a quiet summer evening. Yet this shimmering closeness is a gentle illusion. In truth, the stars nearest to us sit so far away that even the fastest spacecraft humanity has ever built would need thousands of years to reach them. Our cosmic neighbourhood, though beautiful, is not a cluster of friends gathered around a lantern. It is a sparse archipelago of lonely lights, each separated by deep oceans of space. To understand this, let's begin with the star that sits nearest to our Sun, Proxima Centauri. Its name means the closest. But that closeness is only true in a cosmic sense. In human terms, Proxima might as well be on the other side of eternity. It lies more than 4 years away at light speed, meaning that the glow we see from it tonight left the star more than 4 years ago. If you could ride on a beam of light, travelling at the universe's absolute speed limit, you would still need more than 4 years to arrive. And if you travelled on anything we can build today, rockets, probes, even our fastest experimental craft, you would not arrive in 4 years. You would not arrive in 40. You would not arrive in 400. Using speeds achievable by current technology, the journey to Proxima Centauri would require tens of thousands of years, longer than all of recorded human history. The entire rise and fall of civilizations would unfold while your spacecraft quietly drifted toward a single star in the dark. This distance is almost impossible to hold in the mind. To make it gentler, imagine Earth and the Sun as 2 small lamps in a vast field. Now imagine Proxima Centauri as another lamp placed many fields away, so far that even shouting would not let your voice reach it. The space between these lamps is not filled with objects or obstacles. It is simply distance, empty, silent, waiting. Proxima Centauri is not alone. The stars in our immediate neighbourhood form a sort of scattered cluster, though the word cluster may suggest more closeness than actually exists. Barnard's star, for example, lies a little farther out. It is a small, faint star, the kind that would be nearly impossible to notice without powerful telescopes. Despite its nearness, the light you see from it tonight left the star, almost 6 years ago. It is racing toward us across darkness so wide that even light, the most tireless traveller in the universe, needs half a decade to bridge the gap. Then there is Wolf 359, a dim red star lying nearly 8 light years away. At that distance, the starlight we see now began its journey during moments you may still remember. Birthdays, school days, quiet mornings. When you look at Wolf 359, you're looking at a memory of the star, not its present. You're looking at 8-year-old light. And of course, there is Sirius, the brightest star in our night sky, shining with a brilliance that catches the eye immediately. Its glow feels so strong, so present, that it is easy to imagine it as a close companion. but Sirius is more than 8 light years from us. The shine that adorns winter evenings left the star when you were younger, travelling across empty space with perfect steadiness before finally reaching your gaze. What makes these distances truly astonishing is not just the raw numbers, but what they imply about our place in the galaxy. The nearest stars sit in every direction around us, but they are not arranged like houses on a street, or even villages across valleys. Instead, they are scattered like small islands in a vast silent ocean. You could sail for weeks between islands on Earth, but in space, the distances are so great that even light, the fastest traveller we know, moves slowly when measured against them. Imagine floating in a small boat surrounded by a night so dark the ocean seems endless. You know that other islands exist, that other lanterns glow across the horizon, but they are too far to see clearly or reach easily. That is our position within the galaxy, surrounded by neighbours, yet separated by enormous stretches of darkness. Even the idea of visiting these stars or having a conversation with anyone who might live near them becomes a challenge shaped by distance. If an intelligent civilization existed around Proxima Centauri and sent us a message today, we would not receive it for more than 4 years. If we replied instantly, our answer would not reach them until more than 8 years after their original message. That is how long it takes for a simple hello to make the round trip. These delays are not barriers built by nature to keep us apart. They are simply the quiet truth of a universe that stretches far beyond our instincts. The stars are not playing hard to get. They are simply far away in a space too large for our earthborn imagination to grasp without help. And yet, despite these distances, the idea of our stellar neighbourhood remains a comforting one. These stars, though distant, form the cosmic community that surrounds our Sun. They are the closest companions we have in the galaxy, the nearest markers in the sea of night. Each holds the promise of planets, of stories, of light born long ago. Proxima Centauri, for example, is known to host at least one planet, possibly within its habitable zone. The idea of a world orbiting our nearest neighbouring star, just over 4 years away at light speed, feels both unimaginable and strangely intimate. Barnard's star, too, may have planets drifting in its faint glow, and around many of these nearby stars, astronomers are discovering hints of worlds that may be larger or smaller than Earth, rocky or icy, familiar or alien. The more we learn about our nearest neighbours, the more the night sky transforms from a random scattering of light into a map, one that shows not just stars but destinations, possibilities and questions that stretch across time and space. As we drift deeper into this journey, we will explore why travelling to these stars remains so difficult, and why even our best ideas for interstellar exploration require more imagination, patience, and technology than we currently possess. But for now, let the thoughts settle gently. The stars closest to us, though unimaginably far, are still our neighbours in the quietest, most cosmic sense. If you've ever watched a science fiction movie, you've probably seen starships leap effortlessly from one point in the galaxy to another. Smooth arcs of light, instant jumps, bright tunnels folding around the vessel as it races between stars. It all seems so clean, so fluid, so inviting. But the quiet truth hidden beneath these beautiful stories is very different. Travelling between stars is not just hard, it is profoundly, deeply, stubbornly difficult. Not because we lack imagination, and not because we lack courage, but because the universe itself has shaped its distances with rules that cannot be bent by desire alone. To understand why, let's start with something deceptively simple: leaving home. On Earth, escaping gravity feels easy. We climb hills, airplanes lift into the sky, birds glide above rooftops. Gravity seems gentle, almost polite. But this is only because our muscles, our machines, and even our breath evolved inside its pull. When we try to leave Earth entirely, gravity reveals its true strength. Rockets, towering and shuddering with power, burn enormous amounts of fuel just to climb into orbit. Most of a rocket's weight at launch isn't the spacecraft at all. It's fuel. Fuel to push more fuel. Fuel to push past the invisible valley that holds Earth's atmosphere in place. That valley, the gravitational well of our planet, is the first barrier to interstellar travel. Imagine trying to climb out of a deep, invisible bowl. Every step upward requires more energy than the step before it. Reaching the edge is an achievement in itself, and once you escape Earth's bowl, you find that the Sun has a much deeper one waiting. The entire solar system sits inside the Sun's gravity, and climbing out of that bowl demands speeds far beyond what any human currently experiences. The fastest spacecraft we've ever built, the Parker Solar Probe, moves at a speed so astonishing that describing it as a number feels abstract. So instead, imagine a tiny arrow dipped in sunlight and flung around the Sun, gaining speed with each loop until it travels so quickly that continents would blur beneath it if it ever passed close to Earth. Even this incredible craft is moving at less than 1% of the speed of light. In cosmic terms, it is not a sprint. It is not even a jog. It is more like a drifting leaf being carried by a strong breeze, while the universe looks on without hurry. This is the second great barrier: speed. Not because we lack technology, but because the universe has a speed limit, and it is absolute. Nothing with mass can reach the speed of light. As you push closer to that limit, the universe pushes back harder and harder, demanding more and more energy until the requirement becomes infinite. A human-made object can approach that speed, but each step closer requires an almost unimaginable increase in power. The universe enforces this rule gently but firmly, like a parent guiding a child away from a dangerous edge. Yet not all hope is lost. Engineers and dreamers are exploring ideas that float between imagination and possibility. One such idea is Breakthrough Starshot, a project that envisions gram-weight probes, tiny delicate machines no larger than a paperclip, being pushed by a powerful beam of light. Picture a seed carried by wind. These seeds, propelled by Earth-based lasers, might accelerate to 1/5 the speed of light. At that astonishing pace, they could cross the space to Proxima Centauri in about 20 years. Not 20,000, 20. Imagine that. A mission launched in your lifetime could reach another star before you reach old age. But this idea, beautiful as it is, comes with challenges as vast as the journey itself. The beam of light must stay perfectly focused across millions of kilometers. The probes must survive impacts with dust at speeds that turn grains into tiny bullets. And when they finally arrive, they must somehow send information back to Earth, whispering across more than 4 years of light travel distance. These difficulties don't make the dream impossible. They simply remind us that interstellar travel is a conversation between hope and patience. Beyond these ambitious projects lie concepts that belong more to physics imagination than its laboratories. Warp drives and wormholes. A warp drive would contract space in front of you and expand it behind you, allowing the ship to ride inside a bubble, where the universe itself does the moving. A wormhole would bend space like folding a sheet of paper, letting two distant points touch. These ideas are beautiful, like mathematical daydreams, but they depend on forms of energy and matter that we have never seen in nature, quantities that may not exist at all. Still, the fact that physicists can even imagine such things says something wonderful about the human mind. Even when faced with distances too great to cross, we dream of paths that might one day bring the stars within reach. These dreams are not naive, They are a kind of courage, soft, quiet, and deeply human. But beneath every dream sits a simple truth. The universe is vast, and its distances are patient. A message sent to a star will take years to arrive. A starship travelling at speeds we can currently achieve would need generations to complete its journey. And even a ship moving at a fifth of light speed, a near miracle of engineering, would still need decades to reach the nearest star. Interstellar travel is not merely an engineering challenge, it is a philosophical one. It forces us to consider time in new ways. It invites us to imagine journeys that outlast nations, languages, even civilizations. It asks us to think in centuries and millennia, not seasons and years. And it reminds us that the universe is not built for our convenience. It is built for its own quiet, steady unfolding. And yet, there is a strange comfort in this difficulty, because even if the stars remain far beyond our reach, we can still see them, we can still study them, we can still learn their names, their stories, their rhythms. Their light travels freely, carrying with it everything we need to understand the cosmos. As we move deeper into our journey, we will leave the question of travel behind and explore instead what light itself reveals about time, how every star becomes a window into the past, and how the night sky becomes a gentle archive of moments long gone. If you step outside on a quiet night and look up, you might feel as though the stars are shining in real time, as though the universe is happening above you in this very moment. The silver shimmer of Sirius, the steady glow of Vega, the faint blush of distant constellations, they all appear immediate, present, alive in the same night you inhabit. But this is one of the most beautiful illusions the cosmos offers us. The night sky is not a live performance, it is a library. Every star you see is a page from a book written long ago, and the light that touches your eyes tonight may have begun its journey centuries before your grandparents ever breathed their first air. In the sky above you, the past floats like quiet embers. To understand this, let's start with something close to home. When you look at the moon, the soft white glow you see is already a memory, not an old one, just a second or so old, but still a memory. The moon is far enough away that even light, travelling at its unimaginable pace, needs more than a full heartbeat to cross the darkness between its surface and your gaze. If the moon suddenly vanished this instant, which it will not of course, you would continue to see it for a moment longer. Your eyes would still be receiving the last echo of its presence. Now shift your gaze to the sun, the warm light that bathes Earth, that sparkles on rivers and warms your skin on gentle mornings, left the sun more than 8 minutes ago. That means the sun you see in the sky is already 8 minutes in the past. If you held up your hand to block its glare, you would be shading yourself from sunlight that began its journey before you made the gesture. The sun could experience a sudden change at this very moment, and Earth would not know until 8 minutes later. Even our closest star shows us only its recent history, never its present. As we move outward, the delays become more profound. Look to Sirius, the brightest star in our night sky. Its light is dazzling, crisp, almost immediate, but it left the star more than 8 years ago. When you look at Sirius tonight, you're seeing something that happened nearly a decade in the past. Imagine a photograph taken 8 years ago arriving at your door today. That is what starlight truly is, a messenger from distant years. The star Vega sits farther still. Roughly 25 years separate the light leaving Vega from the moment it touches your eyes. The glow you see tonight left the star around the time many adults today were still children, or when world events now considered history were unfolding. If Vega flickered or changed or collapsed in this very instant, we would not know until decades later. The heavens are patient in sharing their stories. And then there is Betelgeuse, the great reddish star resting on the shoulder of Orion. Betelgeuse is a giant nearing the end of its life, trembling with instability. The light you see from it tonight began its journey roughly 550 years ago. When that glow first left the star, the world on Earth was different. Artists in Renaissance cities were painting new visions of reality. Empires were rising and falling. Ships were crossing oceans for the first time. The star you see tonight is not as it is. It is as it was when human history was centuries younger. Betelgeuse may already have gone supernova, may already have exploded in a brilliant burst of light and dust that sculpted new elements into space. But if that happened, we would not know until the burst of light finally arrives, sometime in the distant future. The star could already be gone, and its final message is still travelling toward us, a silent letter written long before our time. This idea that everything you see in the sky is a message from the past changes the night. It transforms every star into a quiet time capsule, every shimmer into an ancient event unfolding long after it has ended. The universe we observe is not a present moment. It is a layered history, spread out across space like a tapestry made of distant memories. Consider standing in a vast, dark library. Each shelf stretches upward into shadows. Each book you pull from the shelf tells a story from a different era. Some are recent, some are centuries old. Some come from civilizations long vanished. The night sky is exactly this library, except the books are stars, and the words are carried to you by the soft arrival of starlight. This understanding brings a quiet wonder. When you look up, you're not just seeing space, you are seeing time. The moon shows you a moment older than your last breath. The sun shows you a moment older than your last stretch or blink. Sirius shows you the world as it was 8 years ago. Vega shows you a time when the world around you was different. Betelgeuse shows you the Earth of the 15th century. When you look at distant galaxies, you are seeing millions, or even billions, of years into the past. You're seeing them as they were long before Earth existed as we know it, long before humans, long before the continents took their modern shape. Some of the faintest galaxies in deep images from powerful telescopes show us starlight that began its journey before the sun itself was born. This is why astronomers say that the farther you look in space, the farther you look in time. Space and time are woven together in such a perfect, quiet union that they cannot be separated. The night sky above you is both a window and a memory, and perhaps the most comforting part of this truth is that you too are part of this tapestry. The photons reflecting off your skin right now will scatter outward, travelling forever into space. Long after you leave this world, the light that touched you will continue its journey across the dark, carrying with it a faint imprint of your presence. In a quiet way, you become part of the night sky's story, part of the library, part of the long and patient unfolding of the universe. As we drift further, we will zoom out even more, past stars and time-delayed light, past constellations and memories, to see the galaxy we call home, a vast spiral river where hundreds of billions of suns drift in slow, majestic motion. When you imagine the Milky Way, you might picture a great swirl of stars, a luminous pinwheel drifting through the darkness. Perhaps you've seen it in photographs, a majestic spiral with glowing arms curled gracefully around a bright centre. But from our vantage point on Earth, nestled deep inside one of its arms, the galaxy does not feel like a pinwheel at all. It feels like a dome of stars overhead, scattered, shimmering, serene. Tonight we'll lift ourselves gently out of that dome and look at our home from a distance, letting the shape of the Milky Way slowly unfold like a lantern-lit river stretching across the cosmos. Let's begin with our own location, a place astronomers call the Orion Arm, The name may suggest something solid, like a limb or a ridge, but it's better imagined as a soft, meandering stream of stars. Our solar system sits along this stream like a modest boat. All around us, thousands of stars drift through space in slow, elegant motion, each one following its own orbit around the galactic centre. Most of these stars are too faint, too distant, or too obscured by dust for our eyes to see, yet they surround us entirely, forming the quiet neighbourhood of our cosmic home. Now, let's pull farther back. From a distance, the Milky Way reveals itself as a spiral galaxy roughly 100,000 light-years across. That number is so large it barely behaves like a number anymore. Even if you travelled at the speed of light, something no object with mass can do, you would need 100,000 years to cross from one side of the galaxy to the other. Every step of that journey would carry you past stars older than your imagination can hold, and clouds of dust where new suns are quietly forming, and yet from above, the Milky Way looks peaceful, almost delicate, as if drawn with soft strokes of light. Our sun, though important to us, is not special within this colossal structure. It is an ordinary star among hundreds of billions. In a panoramic view of the galaxy, it would be less than a fleck of light, one small point among countless others. Its true significance lies not in its brightness, but in the life blooming around it, life that has given us the ability to see, to wonder, and to trace our place in the galaxy all the way back to ancient starlight. The sun itself is in motion, drifting around the galactic centre at a pace of about 230 kilometers per second. That number may sound abstract, so imagine it as a quiet, perpetual glide. Even at this astonishing speed, fast enough to cross continents in the blink of an eye, the Sun still needs roughly 225 to 250 million years to complete a single orbit around the galaxy. The last time the Sun was in its current position, dinosaurs were beginning to roam the Earth. Entire eras rise and fade during one galactic year, and all the while the stars around us shift like grains of sand swirling in a gentle tide. Some of these stars host fascinating worlds. The TRAPPIST-1 system, for example, lies roughly 40 light-years away, a distance far beyond our reach, but close enough for telescopes to peer at with growing clarity. This tiny, dim star is orbited by 7 small planets, 3 of which sit in a region where temperatures might allow liquid water to exist. In that system, the planets orbit so closely that if you looked at the sky from one of them, the neighbouring planets would appear large, bigger even than our moon appears from Earth. It would be a sky filled with worlds, and TRAPPIST-1 is only one example among many. Astronomers have discovered more than 5,000 confirmed exoplanets, worlds circling distant suns. Some are gas giants larger than Jupiter. Some are rocky spheres smaller than Earth. Some orbit in searing heat, while others drift in deep cold. Some circle their stars in a matter of hours. Others take years. With each discovery, our mental map of the galaxy grows more detailed. The Milky Way, once a hazy band of light, now reveals itself as a vast archipelago of star systems, each with its own assortment of planets, moons, and mysteries. It is tempting to imagine the galaxy as bustling with activity, with civilizations and starships and stories unfolding in every direction. But when we step back even further, the truth is quieter. The Milky Way is enormous, so enormous that even with billions of stars, the space between them is almost entirely empty. Each system drifts in solitude, like lanterns floating on a nighttime river, visible to one another yet separated by distances so great that communication becomes a matter of patience measured in years. And yet this emptiness carries a strange comfort. It gives each star room to shine, each world room to turn, each system room to evolve in its own way. The vastness is not a void but a canvas, one where light paints slowly, steadily over billions of years. As you picture this spiral galaxy, its arms curling gracefully, its stars drifting in slow orbits, its worlds circling their distant suns, remember that this is your home. A home so large you could not cross it in 1,000 lifetimes. A home so old its first stars kindled when the universe itself was young. A home filled with histories written in the glow of ancient starlight. And somewhere in one of those arms, on a small planet lit by an ordinary star, you're listening to a story about the Milky Way, using starlight and memory to trace your place in a galaxy that has been drifting quietly for billions of years. Soon, we will drift beyond this home entirely. We will look at how galaxies are arranged in the wider universe, how they gather in clusters, how they stretch into filaments, and how unimaginable voids open between them like vast, silent chambers. But for now, let the image of the Milky Way rest in your thoughts, a spiral river of light carrying us through the night. If you could lift yourself far beyond the Milky Way, far beyond its spiral arms, past its drifting stars and nebulae, you would find that our galaxy is not floating alone. It is one bead in a vast cosmic tapestry, one cluster of light in an immense, intricate structure that stretches across the universe. But even this picture, grand as it is, hides a deeper truth. The universe is not a static canvas. It is stretching, quietly, steadily, delicately, and on scales so large that the stretching of space itself becomes one of the most important stories ever told. To understand this expansion, imagine a loaf of dough rising in an oven. At first, the raisins inside sit close together, but as the dough expands, each raisin grows farther from the others, not because they are moving on their own, but because the dough itself is stretching beneath them. The universe, in a very gentle sense, behaves the same way. Galaxies drift apart, not like ships sailing away under their own power, but like raisins carried by the rising dough of space. Of course, galaxies still have their own motions, small dances caused by gravity, but the overall expansion comes from space itself stretching. This is not something our senses can feel. It doesn't pull your arms apart or make the Earth grow wider. The scale is far too enormous for everyday experience. The expansion becomes noticeable only when you step back far beyond our galaxy, far into the wide quiet where galaxy clusters drift in slow motion. What is truly astonishing is the size of the observable universe, the part we can see. From Earth, in every direction, the universe appears to stretch about 46 billion light years before fading into darkness. That number is so immense it feels like a kind of dream. It means that the most distant light reaching us today began its journey billions of years ago, when the universe was young and the first galaxies were just beginning to form. But here's a quiet twist. The distance to these galaxies isn't simply 46 billion light years. As the light travelled toward us, the universe continued expanding. So the galaxies that sent that ancient light are now much farther away than they were when the photons began their journey. Space has stretched beneath them like dough rising around raisins. Their true distance today, if you could somehow measure the space between, is even larger. This is why astronomers often speak not just of distance, but of look-back time, how long the light has travelled, and of cosmic horizons, boundaries beyond which light has not yet had time to reach us. Imagine standing in a vast field at night holding a lantern. The darkness stretches in every direction, but you can see only as far as your lantern allows. Beyond that circle lies more field, more land, but it is hidden from your view. The observable universe is like that circle of light. expanding slowly as more ancient light finally arrives. The galaxies within that circle are arranged in patterns so grand and delicate that it's hard to believe they formed naturally. They gather in long, branching filaments, cosmic rivers made of stars and dust, and between these filaments lie enormous voids, vast pockets of emptiness spanning hundreds of millions of light years. If galaxies are lanterns floating on a dark sea, then these voids are the calm, dark spaces where no lanterns drift at all. The entire structure looks like lace stretched across nothingness, delicate and intricate, glowing softly in the darkness. These patterns did not arise from chance. They formed over billions of years as gravity pulled matter into strands and clusters, leaving behind the deep voids where little gathered. When astronomers map these structures, the image resembles a giant web, sometimes called the cosmic web, spanning the universe on its largest scales. It is a structure far too vast to see with the naked eye, but one that telescopes and surveys have traced carefully, revealing the gentle architecture of existence. Now you might wonder, if the universe is expanding, why doesn't everything stretch? Why don't atoms, planets, or even people grow wider? The answer lies in the strength of forces at small scales. Your body, your home, your planet, gravity, electromagnetism, and atomic bonds hold everything tightly together. Space stretches, yes, but these forces are stronger. It's only when you move to truly enormous distances, millions of light years, where gravity's hold becomes faint and the expansion of space becomes noticeable, gently pushing galaxies apart. This expansion leads to one of the most poignant truths about the universe. Some parts of it will remain forever beyond our reach. There are galaxies so distant that their light, even if it travelled toward us for all of time, would never arrive. The space between us and those galaxies stretches faster than light can cross it. This isn't because the galaxies are exceeding some cosmic speed limit. Nothing is breaking the universe's rules. Instead, it is space itself that expands, carrying the galaxies away like driftwood on a widening river. These unreachable regions form a kind of cosmic horizon. Beyond this horizon lie parts of the universe we will never see, never study, never know. They exist, but they are forever hidden, like rooms at the far end of a palace whose doors will never open to us. The idea is not sad, but quietly humbling. The universe is so vast, so patient, that even light, our fastest messenger, cannot explore it all. Every star you've ever seen, every galaxy ever photographed, every field of cosmic dust illuminated in golden hues, all of it exists within this observable sphere, and beyond it lies an even greater expanse, unlit and unreachable, stretching far into a darkness that no measurement can ever fully reveal. As you sit with this thought, something soft and gentle emerges. The universe is expanding, yes, galaxies drift apart, horizons shift, but you, and everyone who has ever looked up, are inside one glowing bubble of light and history, connected to distant stars through ancient photons that have travelled for billions of years to reach your eyes. Soon, we will let this understanding lead us into an even quieter truth, that most of the universe is not filled with galaxies at all, but with emptiness. Vast, serene emptiness that stretches between clusters like silent, dark oceans. If you could drift through the universe on a quiet, invisible current, floating far beyond the Milky Way, past neighbouring galaxies, past the clusters where thousands of galaxies gather together like glowing cities, you would eventually enter a region where the lights begin to thin, slowly at first, then dramatically, and finally, completely. You would find yourself in a space so empty, so utterly quiet, that the nearest galaxy might be hundreds of millions of light years away. These places exist. They're called cosmic voids, and they are among the most haunting and beautiful features of the universe. When we speak of the universe being vast, it's easy to imagine it filled with stars, planets, nebulae, spirals of brilliant gas, and glowing clusters. After, all the images we often see from telescopes focus on the luminous parts, the radiant points, the swirling colours, the dramatic shapes. But in truth, most of the universe is not made of stars. Most of it is emptiness. Not simple spaciousness, but staggering cathedral-like emptiness. The kind that makes even the Milky Way, enormous as it is, seem like a small pocket of light nestled inside a void so large it almost defies imagination. To understand these voids, imagine the cosmic web we touched on earlier. Long, delicate strands of galaxies stretching across the universe, forming filaments that intersect in glowing clusters. These filaments are like the beams and supports of a vast structure, a scaffolding of matter pulled together by gravity over billions of years. But between those beams lie wide, silent chambers, regions where gravity gathered almost nothing. These chambers are the cosmic voids. A typical void might span hundreds of millions of light years across. To put that in gentler terms, imagine a sphere so large that light, moving at its relentless pace, needs hundreds of millions of years to cross from one side to the other. Inside such a space you might find a few lonely galaxies drifting quietly, like lanterns lost in an enormous dark hall. But many voids are almost completely empty. They are not simply sparsely populated, they are truly deeply vacant. It's natural to wonder why such emptiness exists. Why would the universe, with all its mass and energy, leave such vast regions unlit and untouched? The answer lies in the earliest moments of the cosmos. After the universe's birth, matter did not distribute itself evenly. Slight ripples, tiny differences in density, caused some regions to attract matter more strongly than others. Over immense spans of time, dense regions grew denser, becoming galaxies and clusters. The empty regions grew emptier, becoming the voids. The universe, without intending to, sculpted itself into a pattern of islands and oceans, bright islands of galaxies surrounded by oceans of near-nothingness. What makes these voids emotionally powerful is not merely their size, but what they imply. They show us that the universe is not crowded, it is not busy, it is quiet, it is still. Even the places filled with stars are mere pockets of light suspended in a much larger sea of darkness. For every glowing galaxy we can see through a telescope, there are uncountable stretches of space where nothing shines at all. And yet, in this great emptiness, there is a certain serenity. If you could drift inside a cosmic void, you would experience a loneliness so complete it might feel spiritual. There would be no planets, no stars, no dust clouds, no light, only the faint glow of distant galaxies, so far away they might as well be memories. You would float in a place where silence is not just the absence of sound, but a presence in itself, soft, infinite, unbroken. This loneliness is not something to fear, it is something to contemplate. It reminds us that our home system, with its warm sun and familiar planets, is an improbable oasis, a fragile bubble of light inside a universe where even galaxies can be separated by vast deserts of emptiness. The Milky Way is just one such lantern, burning gently within the darkness. Consider for a moment how this shifts our view of our own existence. When we look at the night sky, we see countless stars, but those stars fill only a tiny fraction of space. If you could compress the entire universe into a map and highlight only the regions with galaxies, the map would look like a lace cloth stretched across a black table, thin strands of brightness, surrounded by immense fields of nothing. This understanding helps explain why meeting other civilizations, if they exist, may be difficult. Not because life is rare necessarily, but because distance and emptiness define the universe more strongly than closeness or connection. Even if the galaxy were full of life, the spaces between civilizations might be so vast, so empty, that their signals fade before they reach another world. The voids are not hostile, they simply are. They remind us that the cosmos values patience above all things. And there is another layer to this quiet emptiness. These voids also tell us something about galaxies themselves. They persist not because space is crowded, but because gravity clings tightly to the matter within them. Each galaxy, including our own, must fight a subtle battle against expansion. Inside the galaxy, stars remain bound together, but beyond its edges, the stretching of space becomes dominant. Galaxies drift apart, carried by the expansion like leaves floating on widening water. Knowing this, the voids become both haunting and poetic. They mark the places where light rarely ventures. They reveal the true scale of the universe, not the scale shown in pictures, but the scale experienced by light itself. They show us that the universe is shaped as much by what is absent as by what is present. And yet, somehow, amid all this emptiness, you are here, a consciousness made of stardust living on a small blue world, orbiting an ordinary star in a quiet arm of a spiral galaxy. One flicker of awareness in a universe mostly silent. That awareness matters. It allows you to look into the voids and see not fear, but perspective. An invitation to understand how rare, how remarkable, and how fragile every pocket of light truly is. As we drift into the next session, this understanding of cosmic emptiness will gently carry us toward a deeper question. If the universe is so vast and so lonely, where might other civilizations be? And what does a light year mean when contemplating the silence of the stars? If you've ever stepped outside on a clear night and gazed at the sky, you may have felt a quiet intuition rise within you, a gentle certainty that the universe, so vast and so old, cannot possibly be home to just one thinking species. With hundreds of billions of stars in our galaxy alone, and trillions of galaxies beyond that, it seems almost inevitable that somewhere, on some distant world, minds have flickered into existence just as ours have. Minds that wonder, explore, dream, question, and look upward at their own night skies. And yet, we hear nothing. This soft contradiction, the feeling that life should be common, contrasted with the silence we actually observe, is the heart of the Fermi Paradox. But to understand this mystery, in the calm, bedtime-friendly way our journey requires, we must look at it through the lens of light years. Because once you truly understand what a light year means, the silence of the universe begins to feel less like a mystery and more like a natural consequence of distance itself. Let's start with something small and humble, the bubble of radio waves that surrounds Earth. For a little over a century, humans have been unintentionally leaking signals into space. News broadcasts, music, radar pulses, television shows, even the faint static of early transmissions. These signals travel outward at the speed of light, forming a sphere that grows by 1 light year each year. After roughly 100 years of broadcasting, that sphere has expanded to a diameter of about 200 light years. 200 light years sounds enormous. It sounds immense, like a grand accomplishment. But when compared to the galaxy, 100,000 light years wide, it is barely a whisper. Imagine standing in the center of a colossal forest and speaking softly. Your voice travels outward, fading, dissolving into the air long before it reaches the trees at the edge. Earth's radio bubble is that whisper, one so small that it has touched only a tiny fraction of the stars around us. and even within this small bubble, signals weaken quickly. As they travel, they spread out like ripples from a pebble dropped in water. After just a few light years, the signals become faint, fragile things. After a few dozen, they blend into the natural hum of the universe. Even if a technologically advanced civilization sat 50 light years away, they might not notice us at all. Our presence, in the grand and quiet mathematics of distance, dissolves into background noise. Now imagine another civilization living around a star 100 light years away. Suppose they began broadcasting their own signals around the time of your great-great-grandparents. Even if they aimed a powerful message directly at Earth, we would still need a full century for it to arrive, and if we replied immediately, their answer would not reach us until another 100 years had passed. A simple conversation, a single exchange of hello, would take 2 centuries. In such a slow dialogue, civilizations might rise and fall before the second message ever arrives. Empires could crumble, languages could shift, or a planet could face environmental changes long before a reply is received. Time, not technology, becomes the true barrier. It is not just space that separates civilizations, but history. Now stretch this idea further. Imagine a civilization 2,000 light years away. Light from their planet began travelling long before Rome rose, long before the pyramids were ancient, long before human civilization took shape. If they had sent us a message in those early days, we would only be receiving it now. An echo from a civilization that might have vanished or transformed thousands of years ago. And if we responded tonight, they would not hear from us until thousands of years in their own future. When distances are measured in light years, even communication becomes a form of time travel. You're not speaking to someone out there, you're speaking to someone back then. This leads to one of the gentlest explanations for the Fermi Paradox. The universe may not be silent at all. It may only appear silent because the voices are simply too far apart to hear one another. Civilizations could be scattered across the galaxy like lanterns in a vast, fog-covered valley, each shining brightly in their own time, but with their lights fading long before reaching the next ridge. Consider too the lifespans of civilizations. Human civilization, the part with cities, writing and shared stories, has existed for only a few thousand years, a blink on cosmic scales. Our technological phase has spanned just over a century. 1,000 years from now, what will humanity look like? 1,000,000 years from now? We do not know. Civilizations may be brief flares of awareness, shining brightly for a short time before fading. If 2 civilizations do not overlap in time, if one rises after the other has fallen, they will never hear each other's voices no matter how advanced either becomes. This idea is known as temporal isolation. Not only are civilizations separated by physical distance, but they are separated by different chapters in cosmic history. Their stories may never intersect, even if they occur in the same galaxy. And so, when you look up and see the quiet sky, you're not seeing an empty universe. You're seeing light that left other worlds long ago. You're seeing events that occurred before your ancestors ever walked the earth. You're seeing fireworks that may have once illuminated alien skies. Fireworks whose echoes, if ever sent intentionally, may never reach us. The Fermi Paradox becomes softer, more gentle when viewed this way. The silence is not a sign of loneliness, nor a sign that life is rare. It is a product of light years, vast distances that stretch not only across space, but across time. It is a universe where messages are patient, and listeners must be even more patient still. Perhaps somewhere, in a distant star system, another species has looked into their night sky and wondered the same thing. Perhaps they have asked why the universe seems so quiet. Perhaps they have sent messages into the dark, hoping that someday Somewhere someone will hear. And perhaps one day, far in the future, our worlds will exchange their first quiet greetings. Not with urgency, not with haste, but with the slow rhythm of cosmic time. If you imagine travelling to another star, you might picture a long journey, perhaps something that takes years or decades. But what if the journey, at least for you, didn't feel long at all? What if time itself softened around you, stretching for the universe while remaining gentle and short for your own experience? This idea may sound like fantasy, but it is a real effect of moving near the speed of light. It is called time dilation, and it turns interstellar travel into something strangely beautiful, strangely sad, and unmistakably real. Let's begin with a simple picture. Imagine you're walking along a quiet path holding a small lantern. As you walk faster, the lantern grows brighter. You walk faster still, and the world around you seems to shift slightly, the wind brushing against your face more urgently. This is not how time works, of course, but it hints at something true. As you move faster and faster, the universe begins to treat you differently. According to the rules of the cosmos, the faster you travel, the slower your personal clock ticks compared to someone remaining still. Time does not break or tear when you move quickly. It simply bends around you, gently changing its rhythm. And as you approach the speed of light, this bend becomes dramatic. Imagine setting off on a spacecraft capable of flying very near the speed of light. Let's say, a speed where you feel just a few months pass during your journey. You leave Earth behind, heading toward a star 10 light years away. From your perspective inside the spacecraft, the trip feels brief. The hum of the engines is steady, your routines are calm, the months slip by like pages in a slim book. Perhaps you eat breakfast, watch the stars drift past like silver flecks, take a nap, and soon you're nearly there. But back on Earth, almost 20 years have passed. Your personal time and Earth's time have parted ways, not through magic, not through science fiction, but through the natural and very real stretching of time that occurs when you move near the cosmic speed limit. Now imagine taking a longer journey, one spanning 100 light years, a distance so vast that even starlight needs a full century to cross it. If you travelled close enough to the speed of light, you might feel only a few years pass. You would step into the spacecraft in the world you know, and step out into a world so far in the future that your home, your family, your country, your language, and every part of the civilization you left behind have changed beyond recognition or disappeared entirely. This is why time dilation is often described as a one-way ticket to the future. You cannot use it to go backward. You cannot use it to send messages to the past, but you can, in a soft and quiet way, skip ahead. You can drift through time like a leaf floating down a long river, emerging in a world that has flowed far beyond the one you left. Time dilation has been tested, not on starships of course, but in the careful measurements scientists have made with fast-moving particles, atomic clocks in airplanes, and satellites orbiting Earth. In each case, the faster-moving clock ticks more slowly compared to the clock at rest. The effect is small at low speeds, but grows dramatically at speeds close to light. This gentle bending of time is woven into the universe's fabric, is natural as the pull of gravity. But while the physics is fascinating, the emotional truth is even more striking. Picture a traveller on a journey to a distant star system. They accelerate near the speed of light, see only a few years pass, then return. When they step out of the spacecraft, centuries might have gone by on Earth. Generations have lived and died, cities have risen and crumbled, technologies unimaginable have become ordinary. The traveller is not a time tourist. They are a visitor from the past, arriving unchanged in a world that no longer remembers them. This is the quiet sorrow and quiet wonder of relativistic travel. It grants you a view of the future but denies you the world you once knew. It is both a gift and a separation. And yet, there is something strangely comforting in this idea. It means that the universe allows movement through time in a way that imagination alone could not have conceived. It means that time is not rigid. It is gentle, flexible, patient. It allows travellers to drift along its currents at different speeds, each following their own path through the cosmic river. Still, time dilation does not solve the problem of communication. If you send a message from your spacecraft while travelling near light speed, the message still moves at the speed of light, not at the bent pace of your own personal time. If you're 10 light years away, your message still needs 10 years to reach Earth, even if you feel only months have passed. Time dilation may make travel shorter for you, but it does not shrink the space between stars. And so we find ourselves in a quiet paradox. Interstellar travel may be possible in ways that feel miraculous, ways that let travellers arrive in far distant futures. But travel does not create connection. The universe holds its distances steady, its silence undisturbed, its light years unbroken. For a moment, imagine a crew setting out on a long journey, one that feels like a handful of years for them, but spans centuries for the civilization they leave behind. They're explorers of distance, yes, but also explorers of time. Their story becomes a thread woven differently into history, crossing centuries in a single lifetime. Their voyage is not just through space, but through epochs. As we drift into the final session, we will gather all these ideas, the distances, the silence, the vastness, the loneliness, the wonder, and reflect on what it means to be a fragile species living inside an enormous night. A species that measures distance in years of light, and yet carries its own small lantern of awareness into the dark. When you step outside and look up at the night sky, you might feel something ancient stir within you, a quiet mix of wonder and smallness, a recognition that you're standing on a tiny world drifting through an ocean so wide that even light, the fastest thing we know, struggles to cross it. After all the distances we've explored, all the time delays, all the empty spaces, one truth becomes gently undeniable. Humanity is a fragile species living in an enormous night. But fragility does not mean insignificance. In fact, our smallness gives our existence a kind of meaning that vastness alone cannot erase. Consider for a moment the idea of interstellar colonies, small groups of humans or their descendants setting out to settle worlds orbiting other stars. At first, this dream feels hopeful, even joyful, new horizons, new cultures, new beginnings. But then the light years between stars reveal their emotional truth. A colony 4 or 10 or 20 light years away would be separated from Earth, not just by distance, but by time. Messages would arrive years late. Questions sent from Earth would reach the colony long after circumstances had changed. A plea for help might arrive only after the crisis had passed. Even laws or decisions sent from one world to another would become meaningless by the time they crossed the darkness. In such a universe, true governance between stars becomes impossible. A colony cannot wait years for instructions about emergencies, conflicts, or celebrations. It must learn to stand on its own, to grow its own identity. Over generations, these distant settlements would drift culturally as well as physically. Their stories would diverge, their traditions would shift, their languages would bend into new forms. They would not forget Earth, but they would no longer be Earth. In the quiet math of light years, separation becomes destiny. Now imagine a generation ship, a vessel built to travel slower than light, carrying families who would live and die, without ever seeing the destination their ancestors chose. The first generation would depart filled with purpose. The second might grow up inside a vessel that feels more like a world than a ship. The third might question whether the destination still matters. The fourth might barely remember the world that launched them into the dark. Such a journey asks a profound question. Can a mission survive across time longer than memory itself? The answer is uncertain, but the very fact that we can imagine it, the fact that humans can conceive of journeys longer than history, reveals something beautiful about our species. We dream in scales far larger than ourselves. And yet, despite all this dreaming, despite our longing for other worlds and other skies, we remain anchored here on Earth for now. Our home is a single pale world orbiting a gentle star, tucked into the quiet interior of a spiral galaxy, drifting through the universe. Every human story you've ever heard, every laugh, every tear, every triumph, every sorrow, has unfolded on this one globe. Our entire history is a speck of light floating in an ocean of dark. This might sound humbling, and it is, but there is a second truth hidden inside it, soft and warm. We are small, but luminous. Some of the atoms in your body were forged in stars that lived and died billions of years ago. Some were forged in explosions so powerful that they sent their elements rushing across space until gravity gathered them again to form new worlds. You carry ancient starlight within you. You're made of the universe's memories, and because of this, you're able to look up and understand even a little of the vastness around you. You can measure light years. You can grasp the meaning of thousands, millions, billions of years. You can chart the galaxy and imagine civilizations separated by unimaginable distances. You can think about the universe not as a flat ceiling above your head, but as a deep, time-layered structure filled with drifting islands of stars. No other species on Earth, as far as we know, carries this ability. Deer do not contemplate the expansion of space. Birds do not wonder whether ancient light from distant suns may already be the last messages from stars long extinguished. Trees do not question whether civilizations might exist in the quiet spaces between galaxies. Only humans ask these questions. Only humans feel this mixture of curiosity and longing. Only humans build telescopes and ships and stories designed to reach beyond our world. This too is part of the story of light years. They show us how far we cannot yet go, but they also show us how far our mind can reach. Even if our bodies remain bound to Earth, our understanding extends outward across time and space, touching galaxies billions of light years away through the soft arrival of ancient photons. And each photon is, in its own small way, a bridge, a message, a reminder. A star shining 400 years away sends you the light of Shakespeare's age. A galaxy shining billions of years away sends you the light of a universe still in its youth. These messages cross unimaginable distances, not because they intend to. Light has no intention, but because that is simply what light does. It travels. It endures. It carries history with perfect patience. Humanity, like light, carries stories across time. We may not cross the galaxy. We may never reach distant civilizations. We may never bridge the voids between clusters or touch worlds orbiting faraway suns. But we can send our thoughts outward. We can share knowledge, preserve memory, protect culture, and hold on to the delicate flame of consciousness that flickered into existence on this quiet world. And perhaps this is the heart of our place in the universe. Not to dominate it, not to conquer it, but to understand it, to learn, to wonder, to look up at the night sky and recognize that we are tiny, yes, but also aware in a universe that may be filled with silence, not because no one else exists, but because the spaces between us are vast and the speed of light is patient. In that sense, a light year is not just a distance, it is a mirror. It shows us how far we have come from our origins, how limited our reach still is, and how extraordinary it is that a fragile species on a small world can grasp even a fraction of the cosmos that surrounds it. As you sit with this thought, let the image settle gently. Earth, a faint blue dot suspended in the night, circling a quiet star, drifting through a galaxy of slow-turning light. And around this tiny world, a species that dares to measure the universe not in miles or kilometers, but in the time it takes for light itself to travel. A species that listens to starlight as if it were a message from the past. A species that sends its own messages into the dark, hoping someday, somewhere, they might be heard. And above all, a species that understands, however softly, that in the immensity of the universe, knowledge itself is a miracle.